we're piling sand on top of this cone. Okay, so we're going to do this, and as we pour the sand, it's going to keep a 90-degree cone, and the height is increasing at a constant rate of 0.5 centimeters per minute. So we need to figure out what rate of sand do we need to pile on, or the change in volume, when to have that rate of change when the height is 4 centimeters. So first things first, we need to relate the height to the volume. Okay, so how much sand? So height to volume. We know that volume of a cone is 1/3 pi r squared times h. Okay, we've got volume, we've got height. Problem is we've got the radius here of the circle. But we need to somehow kind of figure out, well, how does that fit into the whole picture? Well, if we draw the 90-degree cone here, there's our height, there's a radius. If that's a 90-degree cone, that's a 45-degree triangle. So what we can say in this case is the height and the radius are equivalent. And that allows us then to express this all in terms of height cubed. Okay, now if we want, we could keep this as r, and then we just have to figure out how does the radius change with relation to height. Well, if I want to know that, I can differentiate that. dh by dt is the same as dr by dt. As I have 1 unit change on height, I'm going to get 1 unit change on the radius. Okay, but we don't really need to do that because it's much easier to algebraically replace it. So I've got my expression. I'm going to differentiate with respect to time, and I'm going to end up with pi h squared. Okay, and since height is an embedded function, I'm going to apply chain rule. I've been given that rate. Okay, I know the height is 4 centimeters, and I know the rate of change is 0.5 centimeters per minute, and that gives me 16 times 0.5 is 8, so 8 pi centimeters squared times centimeters is centimeters cubed per minute. That is our dV by dt.